Today we're talking about linear models and direct variation. Okay, we're going to be able to write and graph direct variation and identify the constant of variation for those. So let's look. Your work for a packaging and shipping company. As part of your job there, you are part of a package design team deciding how to stack boxes for packaging and shipping. Because when you're doing this, you want to take up the least amount of space. You don't want boxes just all cat-a-corner and everything like that. So you want to be able to stack the boxes for the best space that you have. Each box is 10 centimeters high, and I show you a little picture here. We're going to complete the table and make a graph of the data points, which is the number of boxes and how high the stack is getting. Okay, so if we don't have any boxes, the stack is not there, 0. 1 box is 10, 2 is 20, and so on. So this should be pretty simple. 3 is 30, 4 is 40. We just keep getting the boxes higher and higher. 5 is 50, 6 is 60, and 7 is 70. So far, so good. Now we need to plot those points. Okay, these are our points. We're going to plot them. 110, 220, 330, 440, 550, 660, 770. How did we go? Yeah, that was about it. You'll notice that it forms a line if we connected them. It's a linear relationship. Write the function to represent the data in the table, and that's in the graph above. Well, your function is going to be f of x. I know that clicking is loud when I'm using the mouse, but just bear with it. F of x is equal to, how many boxes are we doing? Well, that's what changes. That's our variable, x. How high is each box? 10 centimeters, 10x. Okay, our f of x is going to be how high, and the height is going to be equal to 10 times the number of boxes. All right, let's look at number 3. What is a reasonable and realistic domain of the function? Remember, domain is our x values, the number of boxes. We're not going to have negative, okay? There's not going to be a negative amount of boxes. So our domain is going to be more things like 1, 2, 3, 4, 5. So basically, the non-negative integers, okay, includes 0. Our domain is non-negative it's very easier to type this than using this writing tool. Non-negative integers. So 0, 1, 2, 3, 4, 5, 6, 7, 8. Basically the positive numbers. We could have said that. Integers. Non-negative integers. 0, 1, 2, 3, 4, 5. The positive numbers, basically. All right, what's a reasonable and realistic domain for the function? Range for the function. Range is the vertical y-axis, the height. So, not going to have negative here either. We're not going to have a negative height. You're going to go 0, and then it's going to go by tens. 10, 20, 30, 40, 50. So let's see. Our range is going to be 0, 10, 20, 30, 40, and so on. It counts by tens. Okay, that's going to be our range. All the numbers counted by tens from 0 positively. All right, what do f of x y and x represent in the equation. Okay, this is all sort of review. F of x, our function, is how high the stacked boxes are. It's height of stacked boxes. Remember, that is also y. F of x and y are the same thing in this function. F of x or y is the same thing. Okay. Let me just put that as like this, f of x slash y. It's the same thing. For x and x, what does x represent? X represents the number of boxes. Remember, we got all that from the story and from the problem graph. Describe any patterns that you notice in the table and graph representing your function. Well, it does look linear. Okay. Big creasy. The number of boxes is directly proportional to the height of the stack. Use a proportion to determine the height of the stack of 12 boxes. All right, well, we know that one box is 10 centimeters. And we want to set that as a proportion to say how many boxes, or how high is 12 boxes. So x centimeters. When we do our proportions, okay, we can say 1 times x is x, and 10 times 12 is 120. And so 12 boxes would be 120, which does make sense. But we just wanted to make sure that we can use proportions still. Oop. Let's change that to centimeters. There we go, 120 centimeters. When two values are directly proportional, this is a direct variation. Okay, in terms of stacking boxes, the height of the stack varies directly as the number of boxes. Using the variables to represent the two values, you can say that y varies directly. Use your answer in number 6, linear increasing, to explain this statement. As x increases by 10, so does y. Basically, when you multiply an x by 10, your y increases by 10, a factor of 10. All right, direct variation is defined right here. We need to make sure we get this part. As long as k is not 0, and coefficient is going to be k is going to be called, remember, coefficient is the number in front of the variable. It's going to be called our constant of variation. You may have heard it called your constant of proportionality before. Direct variation happens, it occurs when y equals kx. K is just some number, that's our constant of variation. What would the constant of variation be in this function? For number 2, when we wrote it, 10x, 10 is our constant of variation. What do you think the coefficient is called? The constant of variation. Well, remember, think what constant means. It stays the same. Variation is how much it changes. So I think the coefficient is called the constant of variation because it represents that all of the variables change by this same amount. Okay? So it's the amount that it changes constantly. Explain why the value of k cannot be equal to 0. Okay, why did this one say as long as k is not equal to 0? Because then multiplying 0 times anything gives you 0. It wouldn't vary. It wouldn't change. It would just be 0 for every value of x. And that's why k cannot be 0, because then it wouldn't be no direct variation. It wouldn't change. It wouldn't vary. Write an equation for finding the constant of variation by solving this equation for k. All right, well, remember, we're going to solve this for k. Okay, that means I don't want this x here anymore. Okay, so how would I get rid of multiplying k by x? And we do the opposite, the inverse, and divide both sides by x to do that. And so this would go away. X divided by x is 1. You're left with k. Y divided by x would be your answer on the other side. So k is going to be your y divided by x. Interpret the meaning of the point 0, 0 in the table and graph. It's our origin. It's where we're starting from. True or false? Explain your answer. The graphs of all direct variations are lines that pass through the point 0, 0. That's true, okay? If our direct variations is right here, is this right here. If every direct variation is, if this is the definition of direct variation, y equals kx, then all of them, whenever you put 0 for x, will have 0 for y. That'll be all of them, okay? So always the graphs of all direct variations are going to pass through that point. Identify the slope and y-intercept of the graph of the stacking boxes. Okay, well, we had, 10, 20, 30. So our y-intercept is 0. And our slope is rise 10 over 1, 10 over 1, 10 over 1. 10 is our slope. Okay, slope is 10. Y-intercept is 0. Remember, it crosses the origin. Passes through the point 0, 0. That's when x is 0, that's the y-intercept. And then right here, x is 0, the y-intercept is 0. What's the relationship between the constant of variation and the slope? They're the same. Okay, the constant of variation is another thing, and direct variations is the same as the slope. So let's see if direct variation can be used to answer questions about stacking and shipping your boxes. So the height of the boxes varies directly as the number of, so it's going to be written normally. For this type of box, 25 boxes are 500 centimeters high. Find the value of k. Okay, varies directly, direct variation. Okay, we already said that we want to find k is going to have to be y divided by x. So that's how we're going to find k here. Y divided by x. Well, which one of these is our y's and which one of these is our x's? The height is y, 500, and the number of boxes is x. It tells us that in the problem. 500 divided by 25. Okay, what is 500 divided by 25? How many quarters are in $5, basically? Okay. Well, 10 quarters would be $2.50. So we need double that. So we need 20 quarters. 500 divided by 25 is 20. And so that'll be our constant of proportionality. Write a direct variation equation that relates y to the height of the stack. Now that we have our constant proportionality, k, we can just write our equation. Remember, our equation is y equals kx. So now the height is going to be equal to 20 times the number of boxes. How high is a stack of 20 boxes? Okay, it would be 20 times 20. Okay, y equals 20 times 20. And what is 20 times 20? 10 times 20 is 200. 20 times 20 would be double that, so it is 400. 400 centimeters. All right, at the packaging and shipping company, you get paid each week. 1 week you earn $48 for 8 hours a week. Another week you earn $30 for 5 hours of work. Write a direct variation equation that relates your wages to the number of hours you work each week, and explain the meaning of each variable and identify the constant variation. All right. So we know that it's going to be y equals kx. Okay. And we also know some of our points. We know that $48 is 8 hours of work. So I'd say 48 equals k times 8. Okay, we would solve this. 48 divided by 8 is 6. Our constant of proportionality is going to, a variation is going to be $6 per hour you work. $6 per hour. Y is our total amount. X is our work. Okay, number of hours is work, X. Your wages is Y. Constant of proportionality is 6. Variation, sorry. Constant of variation is 6. Remember, constant of proportionality is the same as constant of variation. They're the same thing. Just like slope was the same as rate of change, which is the same as constant of variation and constant of proportionality. A lot of algebra is just different words for the same thing. We just got to learn new words every week, apparently. How much would you earn if you worked 3.5 hours in 1 week? Well, you just multiply our constant variation 6 times 3.5. 6 times 5 is 30. You carry your 3. 6 times 3 is 18 plus 3 is 200. So you'd earn 210 or 21.10 dollars. No, sorry, not 21. $21 is what I'm trying to say. $21. 6 times 3.5 is 21. $21. All right, let's look at some tables, graphs, that represent direct variation, or does not. Okay, does this one represent direct variation? No. How do I know this? It doesn't start at 0, 0. It starts at 3, 0, 3. So that is not a direct variation. Does this one represent a direct variation? It's a straight line, and it does start at 0, 0, so that's a yes. Let's look at the tables. Okay. Multiply this number by 6. Multiply this number by 6. 6. So yes. 2 times 4 is 8. 4 times 4 would have been 16, so that's a no. It doesn't have a constant of variation. The variation is changing. Okay, you're adding what? You're multiplying by different numbers. It's not a constant. Yes, this one is. No, this one's not. It's adding again to it after you're multiplying, so that's a no. Direct variation has to be directly proportional, no additional stuff to it. No pun intended. Okay, constant of variation, easy, 15. Constant of variation, coefficient, 8. Okay, value of x and constant variation is 7. What's the value of x when y is equal to 63? You just need to now divide 63 by 7 to see what the x would have been. Okay, remember it would be y equals kx. You have your y, that's 63. You have your constant proportionality, which is 7. And you just need to know what x is equal. So you divide both sides by 7. Similarly on this one, except now you have your x and your constant proportionality, so you would need to rewrite your equation and just basically multiply 12 times 5. All right, you could use your proportions to get this one. Try number 18 and 19 on your own. But main thing, direct variation has to look like this. It has to be able to be put into this form. Y equals k times x, where k is just some number. That's your constant variation. That's your slope. We just did slope, and this is basically how we're going to continue to define it. Slope for straight lines. For direct variations or straight lines.